It is my privilege to introduce today's speaker, Mr. Indunil Umayanka. Mr. Indunil is a data scientist at PICME Sri Lanka and a former teaching assistant in the Department of Computer Science and Engineering at the University of Moratuwa. He is a motivated data science engineering graduate from the University of Moratuwa, specializing in machine learning and artificial intelligence. With hands-on experience in software development and machine learning, he has contributed to several impactful projects during his internship at CodeGen International. His expertise spans Python, Core Java, deep learning frameworks such as Keras and PyTorch, as well as applications in computer vision and backend systems. We are delighted to have him with us today to share his knowledge and practical insights on building models and handling time series data. Please join me in extending a warm welcome to Mr. Indunil Umayanka. Sir, the floor is yours.
Oh, I think I am audible enough, right? Am I audible?
Yes,
Yes,
sir. You are.
Okay, so good evening, everyone. So thank you for having me in these sessions, and thank you for the humble description about me. And so yeah, let's get started. So I will share my screen. Yeah, let me. So can you see my screen?
Yes, sir. We can.
Okay, okay. So we can get started now. So today, actually, our topic was like time series data and demand forecasting things. So today I will walk you through a real world example that we are using in the Pygmy itself. So, Pygmy is a ride-hailing company that is competing with the major companies like Uber, Hello, and other stuff. So this is a real world product. So actually we are using in our system. So especially I'm going to take you inside the real world deep learning forecasting model. So we will explore how we handle complex time series data to predict ride hailing and demand and supply. So this is just not a theoretical exercise. Actually, it is a look into an engine that helps us to balance our marketplace. So actually, this ensures driver are where they need to be and get you right when you need one. Actually, and so in our next 90 or more than 90 minutes, so let's go through this real world scenario. So I think it is pretty good that you are engaging with this, and so I think chat is available, so you can send me the questions. So yeah, so let's get started. So very basics. So what is time series? So at its core, it's a sequence of value recorded over a period of time. So think of this as the daily temperature or the price of a stock in our case, or in our case, the number of ride requests that we are getting into the system. So what make this time series unique from other data? So there are three components. So here you can see. So very first one is temporal dependency. So what is temporal dependency? Actually, the current value is influenced by the past value. So for example, the demand for the right side, the 8 10 depends on the demand at the 7 a.m. So even the demand at 8 a.m. yesterday will affect the today's demand. So that is what temporary dependence is. So time is the major component in time series data. And next, order. Order is a must. So unlike a simple collection of numbers, you just can't shuffle the time series data actually. So when you shuffle the data, you will destroy everything. So the sequence is the critical to its meaning actually in the time series data. So shuffling the data would destroy every underlying patterns, underlying cycles, underlying every data. So without the time as well as the sequence, time series is nothing. So next one is the patterns. So time series data is rich with patterns actually. So we often see trends like demand growing over the year and the cycles or seasonalities like this demand is spike every Friday. So that kind of seasonalities are there and the other structural changes. So to pretty understand this time series data, so let's compare it with the standard machine learning algorithm. So imagine we are building a standard model to predict house prices. So I think in our semester project also we are doing something like in the our university time. So what we have to do is we have to find the data set and we feed the data set of the house into the any model. So if row one is a mansion in the Colombo and the row two is a small apartment in Candy, actually they are not related. They are not dependent even. So even if you shuffle the data, if this sample data, so hear me out clearly. So if the sample data is unique as well as same, the model will train same thing even if you shuffle the data. But this shatters the assumption in the time series data. Actually, if row one is does not exist, then there is no row two. So actually, the time and the sequence is there. So in the practical analogy, standard machine learning is like trying to guess the genre of the movie by looking at the single row. So imagine we are so for to watch a movie, what we are doing is we are going through various movie banners and checking this one is good, this one is better, or this one is worse. So that is how normal model works. So in time series, when we come to time series model and forecasting, what we are doing is we are just watching the first 45 minutes of the movie, then we are trying to predict the next frames. So what will happen in next frames or something like that. So that is what in happening in the time series data. So that is the basic idea of what time series data is. So we can go ahead and check what is data. So here you can see a real world example from the pygmy itself. So this data is accurately curated. So in this graph shows the demand for rides over 2 weeks. So look closely and you can almost feel the rhythm of the city. So imagine this is from the Moratuwa. So this is the pattern that having the ride request. So the demand. So you can clearly see these daily spikes. So at about 5 p.m. and at about the morning times, school times, and office overtimes. So there are spikes as well as the look at is this there is a daily pattern as well as there is a weekly pattern. So when you look at this weekly data, so you can see in the weekend there is low demand as well as in the weekdays you have a higher demand. So that kind of pattern is there in our data. So this the like the visualization of the data from the pygmy itself. So so what is actually hailing demand and supply? So you might think demand is like having huge requests from the passengers for the requested rides. So yeah, that makes sense. But for precisely, I will explain it that also. So for hailing demand, it is the number of ride requests from passenger in a specific area in a specific time. So we know specific time is like 5 p.m., 4 p.m. or the range of time, a bucket of time, yeah, like a range. But what is a specific area? So actually we are using something called H3 bins. hex bins to map the whole Sri Lanka into H3 bins. So we can divide those area and predict the demand. So that is how we are just specifying the area to the models. So let's talk about more attributes in the later slides. So for now, we keep it in that way. So what is hailing supply? So hailing supply is the number of drivers available and ready to accept those rides in the same area and the time. So it is like you when driver accept those, so we can see the supply. It is same as the concept of buying and selling, something like that. So here it is demand and supply. So actually we are not just trying to predict this. So it is useless actually predicting demand and supply. So we have to have a system. So this the balance between the supply and demand is the healthy ride hailing marketplace constant. So too much demand and not enough supply leads the long wait time. So actually it is from the passenger perspective. When it comes to the driver, so too much supply and not enough demand will lead to a frustrated driver. So that is how so our main goal or our main achievement is to balance these systems, hailing and demand. So that is the basic idea of this. So now we will go to some mathematical concept. So I might sure you are familiar with this concept because I am also a good product from the University of Moratuwa. So I think you are familiar with this. So let's go for time series decomposition. So to understand the pattern in our data, so formally, actually, we can use technique called time series decomposition. So this breaks down the data into a constituent parts. So here we see a base demand and the daily pattern, weekly pattern, and the noise. So actually, I will explain why daily and weekly patterns are there as base and the noise are already there. So base is the long-term underlying level of demand, which we model for constant here. Actually, it is not constant. For it might go up or down, but for simplicity, we have level this to a constant. So for daily pattern, so this is in the previous slide also I showed you. There's a daily pattern. So rush hours is there, like the morning hours there. So we have a daily patterns and as well as the weekly pattern. And we have the noise. So this is very random. So this is what we are trying to predict actually. So noise is the something that we are not aware of with the historical data. That might be a spike, that might be a anything. So that's how we have to decompose this our base demand into four graph. So let's go through next mathematical concept, like we call it time fast time series decomposition, time series to frequency domain conversion. So here, so actually this is another powerful way to analyze time series by transforming time series data in time series domain into the frequency domain. So actually, we are using fast Fourier transform. I'm sure that you are aware of those concepts. So actually, instead of looking at the demand at a point in the time, actually we have the data from the time domain. But for the frequency, we are using this Fourier transform. Then we can clearly see we have huge spikes in the day and 8 hours and weekly. So these are the patterns we used in the above decompositions. So that is how those concepts derived and mathematically curated with the statistics and other stuff. So that is how we are using mathematical, very deep mathematical concept to curate this data into our models. So actually, let's focus like factors influence the demand and supply. So actually, not only drivers and passengers are influenced the supply and demand. That can be any reasons actually. Even it is a time of the day. I mean, in the previous slide also, there is a rush hours in like 5 a.m. in the morning, as well as the locations. I mean, atriums like areas, so tourist areas for the airport, and there those locations are there, as well as holidays or events. If you, for example, if it is a big mesh or anything there, then we have a higher demand as well as the weather. So anyway, weather is a very influencing factor in the demand and supply. So if any passenger who's going to have a bus taking the government's like bus or the uh, going some other from their vehicle, when the weather comes, they are using our platform. So they are booking a ride from the platform. So that means our demands goes high. So that kind of stuff is there in the demand and supply in our platforms. So actually, you might think, we do we have to do this in the machine learning only? So actually, the machine learning is just a tiny part of the whole system. So you have to feed the data, feature engineering, model analysis, everything, and even the visualization part, testing and debugging, monitoring, everything is there. So even though you predict the demand and supply, you can't just take insight from that only. So you have to check the imbalance between these. So I will talk about imbalancing more in the slides. So for now, look at this image also. You can see the ML code is tiny part, but that is a necessary part, but that is not the all the thing. So actually, that is the what ML does in our systems. Actually, you can't just implement the machine learning, then uh, say I am done with the problem or the solution. So that is how industry works. So uh, this is how we productionize the model. So actually, uh, in the industry, we can't just talk with someone and just get into developing the solution, because this is the whole business in the industry. We can see there are stakeholders in various forms, directors, developer side, and business operation, everything, marketing, financial. So we have to get idea from everyone. So very first one is start with the business requirement. So actually, we need to deeply understand what the business needs. So which means looking at it from the all angles, from the all stakeholders angles. In this case, it is about optimizing the experience for both drivers and passengers by predicting demand and supply. So this is the foundation. So imagine we are just talking with few teams and just developing the solution. So what if they say at the end of the solution, this is not what we requested for? So huge cost, huge waste of time and the developer time and business strategies. So whole is gone wrong. So what we have to do is very first, we have to get the requirements clearly. So in here, our demand mainly focusing on balancing the demand and supply. So that is why we have to talk with the business and get the requirements correctly. So next, we have to define the concept and metrics. So actually, these metrics are not the things that we are using in the evaluating the model. This is what we use to align with the business. So imagine how we calculate the success of the model. Imagine we can use mean square error, anything, but how do we communicate with the business? So this is like, so what is the supply from the driver perspective? It is just being the online or being online and available within the specific area in the radius, or and how do we measure success? So we might use mean absolute error for prediction accuracy, but we also need to business metrics. So passenger centric metrics might be percentage of the driver fulfilled within 5 minutes, and the while driver-centric metrics might be average hourly earnings for a driver. So those kinds of stuff are there in the concept and metrics. So next, after gathering the requirements and the alignment, alignment with the business, we can go to the developer side. So very first thing is we know we have a pending data. So but we have to visually see that. So very first one is we doing is with the developer side, we do a EDA, exploratory data analysis. So that is what we have been doing in the previous slide. So we are diving into the data and visualizing, defining the pattern and the features that will be useful. So this is where we get our hands dirty with the data. For example, like during EDA, we might discover that rain, for example, rain increased passenger request demand by 30% in the urban areas, and simultaneously drivers availability will go down by 15%. So that is what we see visually from the data with the EDA. Then we engage with those problems. So we have to sometimes curate data. We have to feed the data from other source. So we have to decide for those. So we have to do a EDA. So next, evaluate the solution. So when we are implementing solution, actually we are not jumping to the very complex solution. In yeah, in Unisys project also, you are not just jumping to the very shiniest or the brightest or the very uh, best tool that we can use. What we are doing is we are just starting from the very basics, like ARIMA or SARIMA models or professional models. So we are just doing simple models and we are checking what we are lacking with those models. Then we are just developing a complex solution to get the better accuracy and the necessary accuracy that we need for the business. So next we build the model. So this is the fun part for developer like data scientists. So what we are doing is training, validating and fine tuning the models on the historical data actually. So here rigorous experiment is the key actually. We have to test everything. So we might train our model on 2 years of data, focusing on how well it will balance needs for both of you. So during the validation, we would check like did the model accurately predict the surge in the passenger demand after the concert ended? Oh, and importantly, did it correctly predict the number of drivers who would naturally migrate to that area? So do we need to build a strong incentive mechanisms? So if we have to, so with this, we can decide that if we need to influence the factors of driver pushing into the high demand area, or they are just going flow with the demand area. So to get a better earning. So we have to check with the models. So that is happening in the systems. So next one is the crucial part, actually the building the MLOps pipeline. So even if we did everything, so gathering requirements, we did everything perfectly, but we cannot do without just putting this ML mods without into production. So we have to build the automated pipeline for data ingestion, training, deployment, and monitoring to ensure the model runs smoothly and reliably in production. So this is the often hardest part actually. We have to automate everything. So in a model in a Jupyter notebook is useless. So for the developing time, we can use the mm, uh, like we can use the uh, notebooks, but when we are using it in the production, we cannot just put the put the Jupyter note in the production. So give me 1 second. Yeah. So that is how uh, we we have production ML building the ML pipelines actually. So we have to monitor the systems, and so we need a monitoring system because when model goes wrong, we have to identify the system. So so Pickney app is the bridge between the passenger and driver. So we have to attend every problem that they are facing. So for that we need a monitoring system also. So everything happen in the ML pipelines. So because of that, this is the hardest part in the productionizing the model. So actually, this is what called attribution. This actually not the only map. So to give you a sense of spatial complexity, so this map shows you how attributes overlay in a city. So each hexagon is a separate area of which we need to generate forecast actually. So for example, for each these hex bins, they are acting very differently. there is a vast difference between these demand and supplies. So we have to divide those area into the attributes, then we can predict. So actually, this is not only a map. This is what we are uh, divide specifically uh, predict into the areas and the time with the time beings. So so now we are coming with the problem actually. So for example, think we have a huge number of models. So that is called the model explosion. So imagine I said we have to predict for each H3 bins. That means we have 1,000 of models. So think about it. In the morning rush hours in the financial district looks completely different from a Friday night near entertainment district. So each X bin has its own unique temporal signature. So a pulse of activity that changes hour by hour. Furthermore, for we add another layer of complexity here. So imagine you can book two or the bike or car from our platform, Pick. So that means not only for H3 bins, we have to predict each taxi type. Imagine we have hundreds H3 bins and 10 types of taxi type. Yeah. So we need to have 1,000 different models. So in here, so that is the model explosion actually. We have huge number of models. So instead of we can't just give whole of data into the model and uh, think it accurately predict for each and every attributes and each taxi type. Instead, we need many specialized models. So this is what we call the model explosion actually. We might literally have a separate model for each key X bins, further divide each specific taxi type. Suddenly, we aren't managing one model actually. So we are managing 100, even 1,000 models. So the challenge becomes an operational one. How do we manage 100 of models without an army of engineers? So we only have like 200 engineers in our Pygmy engineering team. So so actually, how do we attend those models and deal and so monitor those models? So that is the problem we are facing. So that problem is solved with next slide. So actually, we are configuring and training and operation visibility. We have those things in our system. So how do we handle this model explosion actually? So we don't write hundred of different scripts. What we are doing is we are having a unified code base and we are configuring those to train on the specific data for a special area and specific taxi type. So think of like it is a car factory. So in assembly line, you can make a red car or a blue car. So that is not how actually real world happens, but you can make that. So for example, our model differ from two specific reasons. It is from history windows and forecast horizons. So what are these? So history windows means how much past data that specific model need to look at to make a good prediction. For example, a model predict demand in sleepy suburban area might only need 2 weeks, but in a very urban area, we need like 4 weeks of data to check to get the data accuracy from the model. And for forecast horizon is how far we are looking to the future, how far we are predicting it can be 24 hours, 48 hours, or 12 hours, or next hour also. That can be happen. So that is how we differ our model. So after that, after a configuration and the model, we have to do the testing. So now let's talk about one of the biggest pitfalls in engineering phase in the transition from the standard machine learning to time-series forecasting. So it all comes down to how we evaluate our models actually. As you can see in the left side of the diagram, so in the standard machine learning model, we often rely on the k-fold postulation. I might think you are familiar with this concept. So we take our data and randomly scramble it. So we say shuffle in the transformer libraries. Uh, TensorFlow library. So then hold up for like 20 or 25% for testing, and we are training the remaining 80 on the training phase. So this was great actually. So there's no any problems here. So we can do it in the normal machine learning models. But if you do it in the time series model, you will completely own your model actually. Why? Because time has a direction. If you randomly scramble, so if you shuffle the temporal data, you might end up training the model in on December data and then asking to predict it in the October data. So you have a timeline like this. Imagine you have a timeline, then you will train on the last December data, and you are trying to predict the October data. So in here, you have two problems. You cannot do that, as well as here data leakage is here. Actually, you are giving the model peek into the future. So that also a problem. So in the time series data leakage also there. If you shuffle the data, so without that, the way of doing it is the back testing, or we call it a uh, actually data handling through the back testing. This is how we test the model in the time series data. So let's go further. So actually, this is the machine learning pipeline, the automated process that we are working in the uh, demand supply and demand forecasting model. So very first, these are the events that we are triggering to the Kafka servers. You know, Kafka is a publisher subscriber architecture servers. So what we are doing is we trip created, trip started, trip write created data is published into the Kafka. Then from the Apache streaming service, we are just getting those Kafka uh, events from the Kafka. Then we are getting into our raw DBs. Then we are doing feature extraction, and we are making a stage DB that is called where we hold the training data, and we are feeding it to the model training, and we are doing forecasting, and we are checking it is a better accurate data. If it is not, then we are again training model. We are just putting into the older model. So we have a ML4 that model versioning thing, and model versioning tool actually. So after, if the model evaluation is better, then we can put it in the HBase. So we are computing those in the in previous stage, and we are saving in the Apache HBase. It is a row columnar database. So next, we can use demand services and notification service to give it to the driver. So this is how actual the pipeline works in a production environment. So for data processing steps, actually, uh, for assuming we have got our temporal boundaries right. So think we move to data pre-processing. Then there's also for even with the data, there's a or in the computer science we are using is mostly. So if you put the garbage into the model, and the model will output a garbage, there is no better better output from if you input the garbage. So garbage in, garbage out. Neural network is a mathematical engine. So your mathematical engine cannot do anything other than predicting garbage value if you input the uh, garbage values into the model. So actually, we have to do pre-processing to get the garbage value into a better, accurate data set. So first, we have to prepare the data. So we start by extracting relevant data and isolating it by our spatial units, like those tree bins we talked about earlier. So we also ruthlessly drop columns that we don't need actually. For instance, to predict the aggregate demand in the neighborhood, the model doesn't need to know individual user IDs as well as credit card type. So actually, they are useless in the model. So we drop those data columns. and we are getting only the necessary data columns. So next, feature engineering. So this is where we created our time-based features, and there's a critical trick here. So how do we feed time into the neural network? If you just feed the hour into the model like linearly, so imagine you are giving 0 and 20 and 0 from to 23. The model thinks the 20 is far away from the 0. So actually, time is a circular thing. So model needs to learn like 23. Next, it will come the 0, 0th hour. So mean the midnight. So we have to uh, do it with the sine and cosine transformation. So to learn to give this insight to the model, we have to use uh, this cyclic dependency of the time. So what we are doing is we are using a mathematical concept in like sine and cosine transformation with the time, so we can give a better time dependency to the model. So finally, we are normalizing the model. So neural network prefer working with the small and standardizing numbers actually, usually between 0 and 1 or -1 to 1. So if you feed raw numbers where one feature ranges from 1 to 500 and next value ranges from 10,000 to 100,000. So model will be confused and weight will be thrown completely off balance. So what we do is we are normalizing the data. So we scale our numeric features. So that is how we are doing feature engineering. So for example, imagine for a data processing part, we are not quite done with the processing. We have to bridge the gap between our training environment and our live production environment. So we have final two concepts actually. First, we save our statistics. So remember how we just talked about calculating this mean and standard deviation only on the training data. Actually, we can't just throw those numbers away once its training is done. We must explicitly save these normalized statistics, essentially packaging them upright alongside with the model learn weights. So otherwise, we don't know exactly what are those what we have been trained on. So why actually this is important? Because when a live event happen in the production, say a massive search of a passenger open app because it started raining downtown. So model doesn't know understand raw passenger counts. It expects to scale numbers. Our real-time inference engine must take the live data, incept it, and apply the exact same mathematical transformation using those saved historical statistics before feeding it into the model actually. If we lose that stat or if we get out of sync without deploying model version, our production system will spit out garbage again. So we might end up predicting zero demanding hours, rush hours, leaving passengers stranded, and sending drivers to the wrong side of the city. So uh, that is a that is one thing that we save statistic data. So next we have a window and singular row tabular data. So for in the standard tabular ML model, say for extreme boost model, if we customer will churn, the model will look one customer at a time. So it will take this time frame, this one as a one single row, then it will try to predict. But in the time series data, it's not the case. We have to look through the window of time. So imagine we have t minus 1, 2 minus 2. So in previous steps, it like t minus 3, t minus 1, t minus 2. This is how we feed the data into the model. So we call it windowing. So we have a exact uh, window and we are moving it from time to time. So that is how we feed the data into the model. So we talk about this. So actually, this one is going to be a good one. So this is the model architecture. This is the real model architecture that we are using. So even for in the university time, you can use this model for very customized model. So So the model architecture, we are using actually off-shelf basic model. We can't do that because demand and supply is a huge uh, complex problem to tackle. So actually, we are using bespoke deep learning architecture design, especially for chaotic nature of the time series forecasting in the ride-hailing network. So let's walk through this model actually. So in the input window, with the model ingest historical time windows. This is the structured data we just talked about preparing. Says last 40 years, 8 hours supply and demand data for a specific area. So in here we are inputting into the model. Next, we have a convolution 1D layer. The first data, uh, the data first is passes through a 1D convolution layer. Think of this like a magnifying glass scanning over timeline. So they are excellent at picking up local short-term patterns actually. The small kernel. For instance, small kernel convolution 1D layer might immediately recognize a sudden 15 minutes spike in a passenger demand because the local commuter train just unloaded. So a wide kernel one convolution 1D layer might recognize a broader 3 hour difference between the driver supply because their drivers avoiding flooded major intersection. So the small kernel is to sorry the small kernel is to recognize is shorter patterns as well as uh, the large kernel is to predict the get the longer term dependencies like 3 hour, 6 hour, 12 hour, that kind of thing. So next we have something interesting. We are using attention mechanism in our system. So we have a multi-head attentions in so in the data flow into the multi-attention layer, this is the powerful mechanism to borrow directly from transformer models in the natural language proceeding. So this is the same tech behind the large language model like ChatGPT and everything. So does it do for us actually? So it allows us to model learn which part of time steps are most important for making the current prediction, regardless how long ago or they happen. For example, if the model is trying to predict the passenger demand for Friday evening at 6 p.m., the attention mechanism is smart enough to heavily weight the data from the last Friday evening 6 a.m. 6 p.m. actually. So we have this week 6 p.m. and automatically attention layer will give more weight to the last Friday 6 p.m. So actually they are correlated. So in the data we see so that there is a huge relation between those times, weekly and the daily. So what attention does is so they give higher weights and model knows when they are when they are predicting. You have to consider the last Friday to predict this Friday. So next we have a skip connection and layer normalization. So you will also notice a skip connection and so these are standards and essential founding for deep neural networks. So they ensure that the data passes through these complex layers. The model doesn't forget earlier patterns actually. So keeping the training process stable and fast, we are using this skip connection and layer normalization. So next we have a temporal reduction. So in here we have grabbed a lot of data and we have to compress those data. So we cannot just input everything into the model. So we have fed those data and inside them the model what does this is they reducing the temporal data. And next, we have some good fact here. We are inputting the non future features like imagine next Tuesday is a holiday and we know it. So according to the ADA, we know holidays is going to play a different role from other days. So we can give those data as a future data and we know it is a holiday, then model knows exactly where to point from the attention layer. So at the very last steps, so these were the prediction patterns. So we have a dense layer and then output. Finally, all this rich combined information is fed into the dense layer, which produce our final multi-step forecast. So this gives us the actionable number we need, predicting exactly how many rides will be requested and how many drivers will be available over our target time. So that is the overview of our model. And so actually how our model learns these temporal patterns. So let's recap how different apart model works together learn temporal patterns like convolution layer, attention layer, and skip connection layer. So convolution layer is acting as a, like grabbing the small and a large gap between times, as well as attention layers, attention giving weights to the major layers in the major time frames in the our historical data, and script correction doesn't give the aware of the earlier patterns. So this is how convolutional 1D convolution layer works. So I say about the kernel, and we have the filters, and we have this kind of matrix, and it will calculate this kind of uh, output vector in our data also. This is how same concept is applied for our convolution layers. So next we had the attention mechanism. So in here, so the concept, so in this classic example, when processing the word it, self-attention allows the models to understand what it refers to. So in the first sentence, the it refers to the animal. In the second, it refers to the history. So that is how a normal understandable way to say the attention mechanism. So that is the exact way how in our model the attention layer works. So what is attention in the time series section? So when we are predicting the demand for a specific time, some part of hours matters actually. Same time yesterday and the same past hours doesn't matters all at doesn't matter actually. For example, if today is Tuesday and tomorrow is Monday, so sorry, last week's Tuesday, it might be not related, because if today the this week's Tuesday is a holiday, then the whole last Tuesday data is useless in our data. So model has to go to the the previous last day and check whether how it performs, and check whether for a holiday, and they have to give up a better model performance. That is how attention happens in our model. So crucially, the importance of these past hours changes day by day actually. The patterns that matters on a normal Tuesday are different from those on a public holiday. So what is attention? Essentially a learned dynamic weights average over past time steps. So actually uh, each past hour in the input window assign a weight, then important hour get a higher weight, and unimportant hour get a lower weight. So that is how normal attention mechanism works. So actually uh, I talk about a lot about the attention because it is the best mechanism that we have used to get the aware of the time temporal dependency of the data. So actually this is where magic happens. So single model with the same learn weight can exhibit different attention behavior based on the input context. So uh, before deep learning, traditional time series model like ARIMA relies on the fixed legs. So the engineer has to make those features. Imagine you look at like exactly 24 hours ago, and you have to give the features like look exactly 7 days ago. So, but in the real world, the cases are not that rigid. Actually, for example, use the pick me example. So, New Year's Eve. If today is the New Year Eve and we want to predict evening demand, looking at yesterday, like 30th December, is practically useless actually. So, yesterday was a normal login day. So, New Year, you behave completely different. So, this is why we use attention mechanism. So, we don't tell model where to look at exactly. So, we give it a massive window of past data, and the attention layer acts like a spotlight. So on a normal Tuesday, spotlight shines brightly on yesterday, but on the New Year Eve, the model automatically shift its spotlight into the better day. So if it dims the weight of the yesterday and shines the spotlight brightly on the 365 days ago, so last year Eve. So reason and all the reason towers also see how party crowds are built up. So it learns what to care about dynamically actually in the real time. So in the standard machine learning models cannot do that actually. So that is why we have to curate a bespoke model as well as get the attention layer mechanism to into our system to get a better accurate model. So so what this loss does in the model. So this is a good concept actually. Imagine uh, we can use mean squared array anything for evaluation of our model. So what is the impact of using this loss? So during training in our data, uh, like in the to the common view of the loss function is just number that we are minimizing during training, like absolute mean error. But in the real world, loss function is how we define a good predictor. So imagine business need the good metrics to think about the models and the numbers that we are giving. So in the scientific forecasting, not all errors are created equally. So and different errors have every different real world loss cost. So actually in our models, so in our model, we are using asymmetric loss. So we have a symmetric loss. If we are penalizing the model with same weight, or we are penalizing it with the same weight for the errors, that is symmetric. Asymmetric means some cases are prioritized to penalize. So they are given higher weights to penalize, then other cases get lower penalized values to the loss function. So in our models, no, let's talk about the computer metrics first. So I think you are familiar with the computer metrics. So so first thing is spam email filter. If the model makes mistakes and less spam email get into your inbox, false negative, then what is the cost? Actually, it is pretty low, right? So you can delete the email and move on. So, but what if uh, a legitimate email is flagged? So it can be a highly important mail, like a job offer, like a message from your boss. So if you put it, if the spam filter put it as flag it as a spam, then it becomes the false positive. So that cost is huge. So you therefore we are building a spam filter. So you are heavily penalizing false positive. So you tell the model it's okay to let a little spam through the model, but never hide the real email as a spam email. So that is how spam email filter. So next, go to the cancer patients problem. So if a doctor runs a test on and tells a healthy patient they might have cancer, it is a false positive and it causes immense stress and require more testing. But from the patient side, it is not okay and it's not fair. But imagine, but ultimately that is okay, right? The physical is okay, he's not going to die, and patient is okay. But doctor said he's in suffering from cancer, but they get some medicine, that is okay. But what if uh, doctor release a cancer patient saying he's okay? So they have to pay it from their life also. Uh, So that is what we call false negative. So the cause is a catastrophic actually. So disease progress untreated, and in the medical machine learning models, we are heavily penalizing the false negative. So you tell the models it's okay to be overly cautious and run more tests, but never miss a sick patient. So if we miss a sick patient, and we can lose a life also. So that is how in the real world scenarios are prioritizing. In the cancer scenario, we are prioritizing the false negative, and in the spam filters, we are prioritizing the false negative. So we are giving uh, separate values, or you can say we can use recall or something like that matrix. So that is how it works in the real world. So in our case, uh, actually, the during training, under prediction becomes more expensive for the model. So imagine we are telling model to not to be too low when it's uncertain. It will tend to predict slightly higher values. So if the model is not sure about the predicting demand and supply, it will give more higher values than giving a low value. So and the business impact is it is significant actually. It leads to a fewer demand shortage and better operation reliability. If the demand is shorter, then it is okay. If the no, so demand is shorter, there is a huge problem. So because we have a higher supply, then driver will frustrate. So that is a case we are facing with. So in this bring to us the mm, actually the uh, how we are working with the model, the loss, how we define the model losses. So we face the similar asymmetric reality, just apply to the regression instead of classification. So under prediction, the false negative. So if we predict 50 passengers will need ride like rides, but 100 actually shows up, we have a massive supply shortage. So we didn't incentive enough driver to go to that area, and passenger opens there and see no cars available. So there is a problem actually. So immediately, so when passenger sees there is no available vehicles, uh, passengers will jump to the competitors app. So actually, we lost revenue, and worse, we lost the trust with having with the passenger and driver. So it is incredibly costly, actually. And the over predictions, and we call false positive. So if we predict 100 passengers, but only 50 shows up, so we have oversupplied the area. So we have 50 drivers sitting ideal for little time. So this caused some inefficiency. It is true. So actually, driver might earn slightly less for that hours, but it is far less harmful than losing our passenger base completely. So you might think like we are just prioritizing passengers over drivers because we are just prioritizing under prediction over predictions. But uh, it is costly to lose a passenger than the driver, because passenger is the one who is creating requesting rides. So drivers also have rights, because if passenger creates it, so passenger is the one who prioritize in the model also. So with the big business requirements, so standard machine mean scared error like MEA loss function doesn't care about this. Actually, it penalizes predicting 50 two few rights, same as exactly as predicting 50 too many. So it is actually uh, penalizing same the under prediction as well as the over prediction. So in our solution is to mathematically alter our loss function to make it asymmetric. So we intentionally design it to a model is penalized much more heavily for under predicting than over predicting. So this forces the neural network to be more conservative. So when it down, so it will slightly over-index on demand to ensure we always have enough supply to handle to predict the user experience and the business. So this is exactly how attention mechanism works. So imagine, so when we have a asymmetric uh, losses, always attention mechanism knows we are trying to predict over one, always. So it will always give the higher weights to the historical data according to considering with those data. So when the uh, uh, like the demand predicted demand and supply is lower, it is highly penalized. Then model knows this is not okay. Then I have to predict higher value. So that is how attention mechanism, loss, and the feature engineering and the machine learning, and those are working. And I want to consider another mechanism called we have an imbalance calculation process. So what we are doing is first we are predicting demand and supply. So first we are predicting the demand. We are totally depend on the demand. Then with the attention mechanism, it will so not the attention mechanism. So we have statistical data loaded. So we have the demand in the predicted demand, and we can go to the same time frame in the last weekend, so last month. Then we have a same thing happen in the or same thing or some likely about related thing happen in the uh, another day, the same demand. So we have the uh, supply that is handled the this demand from the in the historical data, and we are just comparing the historical supply and the predicted supply, and we are checking the imbalance. So the imbalance is higher, I mean, from the predicted one is lower, then we have to give an incentive and push the drivers, idle drivers from low demanded area to the high demanded area. So that is how the imbalancing works. So to uh, push the drivers from the low demand to the high demand areas, what we are doing is we are having a incentive mechanism. So incentive is what we are giving a driver when they are reaching to the specific area, when they are doing a specific number of hires after the day, or it can be weekly, daily incentives. So that is how we have to work with the real world cases. So when we have to balance two sides like passenger and the drivers, we have two stakeholders. We have to uh, uh, think about both those parties. So we have demand and supply. So we can check whether the driver is ideal or their earning is low. So what we are doing is we are giving, if you go to this area and if you do this much of hires, you will earn like 1,000 more and you will get 5,000 more. So that kind of scenarios are there. So that is how we are doing things in the industry. So I'm not sure you are aware of this concept, because that is how the production world works, as well as that is what business requires. As we, as a developer, we are just only developing the solutions, but business require other stuff. So at the very this is the output of the model. Uh, this is the end result. So in the left side, the blue line on the left side is the historical data the model used as the input. So actually, we are training the model, and we are just input the model 48 hours or 24 hours according to our requirements with the X bins and the time bin. So this is this kind of data, and the green line is the actual one, uh, actual demand that is occurred. So next we have the dash line. Uh, the blue one here is going higher than the predictor may real one. So I think we have just missed this case. So uh, these two one should be changed. Actually, the blue one, the this one is here the predicted one. The green one is the actual one. So I'm sorry about that. So uh, the green one is the actual one actually. So it is going lower, and our model predictor is going higher. So I in the initially I said we are highly penalizing the predictions, undervalue predictions. So here you can clearly see when it is not sure about the demand, it is given a higher value with when comparing to the real value. So that is how the model works. So that is what business needs. So anyone can see the model does a fantastic job of capturing daily pattern, including the morning and the evening peaks. So you can see with the time frames, it really capturing the high demand times and the time in the lunchtime as well as low in the midnight. So that is how the real world model needs to work in. So this is the kind of accuracy that allow us to make smart and data-driven decision in the real time. So with the this kind of model, we can do incentive mechanisms. We can make maps that help the drivers to uh, give more insight on how demand is varying, and that is how a real world model works with the demand and supply. So I might think you got the knowledge about uh, hailing demand and supply, and how we productionize the model, and how we feature engineering, and how tiny is the ML part. So actually, when you are learning in the university, just focus on those things also, because uh, actually only learning machine learning doesn't give you a job. Actually in the industry, you know that the job is actually critically in this field is now a critical job. So you have to think about those also, understand the problem, getting the requirements and the communication skills, as well as the getting the requirements, as well as feature developer part like feature engineering, data ingestions, and how our data should be prepared to input to the model, as well as everything about productionizing, not only the model part, machine learning part. You have to focus on the MLOps pipeline, like machine learning model versioning, as well as the like TensorFlow, PyTorch libraries, and the big data platform tools like PySpark, Spark, Kafka, and everything. So learn about those things when you are coming to the industry, and that is how and actually production world works and the industry works. So actually these are the reference I used in the used when preparing those slides. Actually this is the end actually. So we can have like 10-15 minutes on the Q&A if you have any. So yeah, so that is the end of the presentation actually. So thank you for joining actually. So yeah. I am so very sorry. I just missed the message. Someone. So I think I can provide you with the slides. Actually, I think you can go through those slides uh, and get more knowledge on the modeling part and the attention mechanisms. So actually, I didn't see the message. I'm very sorry. So if you have any other questions, we can discuss it with now, and yeah, we can have like 10-15 minutes on that. Sure, sure. I will share the slides with you. I will share the slides to I think, one of OC member. So they will give you the slides for sure. I will share it. And I think you guys are mostly from 23rd, 24th batch, right? So multiple models. Yeah. What factors should we consider when comparing multiple models? So as I mentioned in the slides also, first you have to try with the very basic models. If a linear model works, then the solution is okay. So when we are going with the experiments, you have to check with the how complex our data set is. So how many parameters and how deep our model should be, uh, and what the model actually our requirement. So in the profile, so what we did in when we are doing here. So imagine there's a model called Prophet. I think it is from Meta, and Prophet model can it is a forecasting model. So what they do is we can uh, input data and train the model. Then it will output the next for a specific time frame that we are asking for. But we can't so we can't just input our last 48 hour or last 24-hour data into the format model, then ask to predict on that. So that kind of business requirements are there. So what we were going to do at that time was we are trying to give the last 48 hours so the model knows better uh, context knowledge because it knows how actually the last 40 years our demand and supply changes. So that kind of concepts are there. So if you are computation power and the cost. Actually, next factor is when we are working in the industry. So mostly this coming with the data engineers. So we are working with the big data. So we have like 10 years of data. So we have to work with a lot of data. So what we are doing is we are we are using Google Cloud Service. We are just spinning the uh, let's call clusters. We have multiple nodes. So we want to work with those and the cost is so high. So I think it is more than like $20,000 per month we are just spending on those computations. So that is two factors like cost and the time you have working on. So think about this is the real time model. So if this is not a real time model, so near real time. So if you need to have a real time model, you cannot go to a very complex or layer mechanism model. So you have to be very small. Each the model should be very small and specific. So when those times you have to check whether it is real time or not. So I mentioned like real time, the cost as well as the complexity of the model concept, complexity of the data, and what you are what is the expectation from the model. So those factors should be considered when you are comparing multiple models actually. So I think I answered your question. So we have a next question. What course or libraries do you recommend for beginners to more explore? Good one. For anyone, so in the industry also, what you expecting is we are just using uh, another customized enterprises level models. Actually, no, we are using transformer and the Spark ML library. So those kinds of models are using. So for beginners, actually read the TensorFlow documentation. So you might not understand everything, even in the our time in the industry also, our team also. I think we cannot understand everything. We can learn everything. So what we are doing is, so actually these days we are implementing a recommendation system. So what we are doing it using the TensorFlow recommenders. So there is a very good, so they have a very good documentation. They have very good tutorials, and the community is very high. So you can get any help from the Stack Overflow, even with the LLM. So they know a lot of things. So you would use not LLM and put the those documentation as the what is called reference. Then you can ask any questions. So that is how I learn also. So watch a YouTube video and everything works, and doing a course everything works. But in now industry is moving so fast. So for the beginners and to learn anything, and now use documentation as well as the LLM platform. So I recommend you transformer library and the that documentation. As for the beginner, it is a better one. Actually, I can't imagine something better than that.
Thank you very much, Mr. Indranil, for that insightful and engaging session. I'm sure everyone gained a better understanding of building machine learning models and handling time series data, along with valuable practical insights and into their real-world applications. As there are no further questions, we will now conclude today's workshop. Once again, on behalf of the IEEE IES Student Branch Chapter, University of Moratuwa, I would like to extend our heartfelt gratitude to Mr. Indranil Umayanga for taking the time to be with us today and for sharing his knowledge and experiences. Your insights have undoubtedly helped us gain a deeper understanding of building machine learning models and handling time series data, inspiring us to continue exploring the rapidly evolving field of artificial intelligence and machine learning. Please accept this virtual token of appreciation displayed on screen here as a symbol of our heartfelt thanks. To all the participants, thank you for joining us and making this session a success. We hope today's workshop has strengthened your understanding and prepared you for the next stages of OctWave 3.0. Stay connected through our official communication channels for updates on the upcoming workshops and competition activities. Have a wonderful evening, stay safe, and we look forward to seeing you at our next session. Thank you, everyone.